Hey guys, welcome to your first lecture from Chem 112. You made it through Chem 111. Woo! So now we're going to start chapter 11, okay? And chapter 11 is entitled Liquid, Solids, and Intermolecular Forces. You can find these notes on Schoology along with this video for your viewing pleasure. Okay, so chapter 11 starts out by talking about the three states of matter, which we've talked about a lot. You've talked about in middle school. So there's nothing new and crazy there. We know that solids are packed really close together. We know that as they melt and become liquids, they swish around and there's a little more space between them. And then as they become gases, woohoo, they're way out away from each other. And we should also know that because those solids are so close together, the attractive and repulsive forces between them are going to be stronger. If I'm standing right beside somebody that I despise, the repulsion is going to be super high. But if that person that I'm repulsed by is in the other classroom, I may still be repulsed by them, but not as much because they're not standing right beside me. The same thing happens with atoms and molecules. Solids are going to have greater intermolecular forces because they're closer together than liquids, and liquids will have greater intermolecular forces than gases because they're really far apart, okay? So distance is going to have a relationship to how strong your intermolecular forces are. Now, as you read this chapter, you probably realized that this chapter covers the same intermolecular forces we discussed last year in chemistry. The first one they call dispersion. Last year we referred to it as London forces. And all molecules have dispersion forces. So if I give you a question and say, what type of intermolecular forces does this have? All of them are going to have dispersion or London forces. They tend to be the weakest, okay? Now, one thing it also talks about, there's a little table in this chapter, and it goes over boiling points and how boiling points are changed. And in general, okay, the more intermolecular forces you have, the higher your boiling point is going to be. And also, you expect your boiling point to increase with molar mass. So, for instance, if you had neon and krypton, and I said, who's got the higher boiling point, just as a generalization, just asking you to hypothesize, you would say krypton, because krypton has a higher molar mass. Another thing you would look at is surface area, okay? So if you have a larger surface area, I'm going to write large surface area, you expect to have an increased boiling point. And in your book, they give you the example of pentane and neopentane. And pentane is a nice molecule that's just laid out like that. And neopentane kind of has a little thing going off of it like that. So the larger the surface area, we expect there to be an increase in the boiling point as well. And in your calculation sheet for this chapter, we're going to have some examples where we kind of beat a dead horse with this to make sure we all get that. Okay? Now, so the first intermolecular force was dispersion. We called it London last year. It's the exact same thing. The second intermolecular force is dipole-dipole. We did dipole-dipole last year. It's when you have a bond between two atoms and they are different, okay? One's a nitrogen and one's a oxygen, okay? You get this kind of shift of electrons. And what happens is you get that partial positive and partial negative charge there because the electron distribution is not equal. So you have a lot of your electrons over here and a little over here. Somebody's a little greedy with the electrons. These molecules tend to be polar, okay? It's a polar bond. And if you see polar molecules, you expect them to have a higher melting point and boiling point. So, for instance, if I gave you a compound, let's do methane. Methane, if you'll remember from Lewis dot structures, is a nonpolar compound. And the reason it is nonpolar is because it is totally symmetrical, okay? Nonpolar compounds, okay, tend to have lower boiling points, okay? Because they don't have that polarity. They don't have that partial positive, partial negative charge inside the molecule. Again, we're going to beat a dead horse with that in your calculation sheet for this unit. Now, I gave you some examples in your notes, and we're going to go over them now on the board, okay? Which halogen has the highest boiling point? Chlorine, bromine, or iodine? Okay? So you have chlorine, bromine, or iodine. Who's got the greatest boiling point? Well, I look at all of their molar masses. This has the highest molar mass on the periodic table. My guess is that that's going to be the highest boiling point. The next one, does carbon dioxide have dipole-dipole forces? Well, carbon dioxide's Lewis dot structure. Remember, to find if something's polar or non-polar, you need to do the Lewis dot structure.
Good morning, King Willie.
That is Coach C. Isn't he just a delight?
Please stand.
Let's go ahead and do our pledgy-poo since they're doing it.
I pledge allegiance
to the flag
of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. Please remain standing for a moment of silence. Ladies and gentlemen, today is a very special day, very important day, should be a national holiday, because it is our All-American nurse, Miss Lewis's birthday. So, if you see her, when you see her, make a trip to see her, not if you're sick, well, probably if you're sick, but make a trip to see her and wish her a happy birthday today, and let's have a great day. Go Cavs.
Happy birthday, Nurse Lewis. All right, so when you look at this Lewis dot structure, it is totally symmetrical. So this Lewis dot structure is nonpolar. So no, it's not going to have any dipole-dipole forces. All right, the next one. Let me go over here. Yep, I got some room. I have to write my Lewis dot structure, which is super easy for super chemists who have finished Chem 111. All right, I noticed that this Lewis dot structure is not symmetrical. If you look at the carbon, there are different items coming off of it. So yes, this is going to be polar, and since it's polar, it is going to have dipole-dipole forces, okay? So we've talked about London forces. We've talked about dipole-dipole forces. Again, nothing new. We did all of those last year, and probably somewhere in the back of your mind, you're thinking of the strongest intermolecular forces we discussed last year, which are hydrogen bonds, okay? Now, hydrogen bonds have to have hydrogen in the molecule. Last year, I told you to remember it as Sun F, okay? And so anything that has sulfur, oxygen, nitrogen, fluorine, your book this year is really more of a ONF. So that's how they're talking about it. Hydrogen bonds are your strongest intermolecular forces, and they do some weird things. They really raise the boiling point. They raise the melting point. So if you have a substance and you recognize immediately that there are hydrogen bonds, like for instance, water is the classic substance. Water exhibits hydrogen bond activity. That's why water's boiling point is so much higher than we expect for a molecule with this mass, okay? Because we have to put a lot of heat energy in to not only break bonds, but break those intermolecular forces called hydrogen bonds that are holding that water together. It is so strong because there's such a big electronegativity difference between that hydrogen and that oxygen. And you've got to rip that attraction apart too, and then make it go into the gas phase, okay? Now, the book does discuss one intermolecular force that we didn't talk about last year, and I'll fix that so this year's honor super chemist will get that. And that is IonDipole Force, okay? IonDipole force occurs when you have an ionic compound mixed in a polar solution. The classic polar solution is water. And hopefully you remember from last year when we talked about solubility, the term like dissolves like. Polar substances dissolve polar substances. Non-polar substances dissolve non-polar substances. So if something doesn't dissolve in water, water's polar, then it must be non-polar. That's why water and oil don't mix, because oil is non-polar, excuse me. Your book then goes on to talk about surface tension, capillary action, a couple of things. Checking my notes. If you have really high intermolecular forces like water, really strong hydrogen bonding, you expect there to be an increase in your surface tension. And surface tension occurs if you take a penny, and a lot of you did this in biology, and you add water droplets to it, and what you find is that instead of the water laying flat on it, it goes up like this. It's almost like the surface creates a kind of skin that resists penetration, and that's what your surface tension is. Water is superpolar. It's a great example of that. As you decrease your intermolecular forces, you do decrease your surface tension in substances. The next item that chapter 11 talks about is viscosity. You know, how thick is something that you're pouring. Think of something like your pancake syrup versus water. Okay, pancake syrup is going to be more viscous, you know, because it's a little slower when it pours. If you increase your intermolecular forces, you're usually going to increase your velocity. If you increase your molar mass, you're going to increase your velocity. If you increase, and all of this is written in your notes for you to look at. And if you increase your temperature, though, you're going to lower your viscosity. And if anybody's ever cooked with syrup or anything, made some good pies, you know when you heat that syrup up on top of the stove, that syrup gets runnier. Okay, so if I increase the temperature, that viscosity is going down. All right, the next thing your book talks about is capillary action. Okay? Capillary action is when a liquid flows against gravity up a narrow tube. If you've ever had your finger pricked for blood, they may have put something there and you can see the blood shoot right up. That's capillary action. If you have capillary action, that means your adhesive forces of that substance are greater. Adhesive meaning that substance is adhering to the glass tubing going up, okay? Cohesive forces are the attractions in the liquids. If your cohesive forces are greater, you're not going to have any capillary action. So you're looking for really high adhesive forces for that liquid to adhere to the walls of that tube and shoot up and defy gravity. And I'm going to end this section talking about vaporization, okay? Vaporization, you guys know, is when we add heat to a liquid and that liquid becomes a gas. Condensation is different. Condensation is when a gas cools down and it becomes a liquid. If I have a cold beverage up here, it's got little water droplets around it, it's condensation, okay? Volatile liquids are liquids that vaporize easily. Like if you've ever gone into a nail shop and had your nails done, it smells like acetone. That's because acetone, as soon as you open the bottle, vaporizes. It's volatile. It doesn't take much energy to make acetone become a gas. I don't have to put much energy in. Non-volatile liquids require energy or heat to turn into a gas. They don't vaporize easily. I can't just set most liquids out in my room and they vaporize right away, like acetone does. There is a brief calculation on this slide about vaporization. Super easy, okay? And so it says that we want to calculate the mass of water in grams that can be vaporized. I have 155 kilojoules. I'm going to use the heat of vaporization to convert that to moles. And then I can convert moles to grams using the mass from the periodic table. And that's how I answer that question. Kind of a quick and easy conversion, okay? I know I ran through that, but I was afraid I was going to hit my 15-minute mark on Screencast-O-Matic, and I didn't want you to miss it. So this concludes part 1 of your Chapter 11 notes. First unit of Chem 112. Welcome back, guys. I hope this was helpful. Can't wait to see you in class. Toodles, poodles.